Hello, my friends of Qatari Labs. Welcome to this tutorial, this webinar. Okay, the webinar that we are going to have right now is webinars, webinars.qatarilabs.com. Okay, we are going to have a regional example of seawater intrusion modeling with MODFLOW6 and mf6Voronoi. Okay, so we have a person here waiting for to be approved. Actually, there was one guy that left. Okay, so let's see. There is a link here that where we are going to find the input file. So we authenticate. The password is Qatari Labs with capital H. Okay, Qatari Labs with capital H. Okay, Qatari Labs with capital H. Yeah, and then we download the zipped file. Okay, once you have downloaded the zipped file, you place it under your documents, and then you extract there. Okay, extract here. Okay, and then you should have something like this. Okay, documents, and this folder of regional seawater intrusion modeling with these two folders. Okay, it has to be like that, documents, regional. Okay, so it's in another level. Please try to make it in this way. Okay, once you have it like this, please type 1. Okay, for the people that follow this webinar, okay, this webinar will be available right away in our Patreon site. So in patreon.qatarilabs, patreon.com/qatarilabs. And if you are not a supporter from us, we strongly recommend that you support us through Patreon, because in order to do this kind of stuff, actually we devote a lot of resources. Okay, and then after some weeks it will be released as a webinar. Okay, great. So if you have the files like this, please type 1. Great, Fatima. Great. Great, Paul. Great, Abdillah. Fatima, from which country you're connecting? Paul and Abdillah. Emiliano, are you there? Okay, great. Okay, great. Okay, great. Okay, Abdillah, from where? From great, in Qatar. Interesting. Okay, so let's have a look on the dataset. Okay, QGIS desktop. and then we are going to explore the raster and data sets that we are going to use to create the mesh, and also the data sets that we are going to use to create the mesh and the model, in fact. Okay. Okay, so my QS is launching, I guess. Yeah. Okay, so let's see about the dataset. Documents, regional seawater intrusion model. We have two catchments. Why we have two catchments? Because this valley, okay, this valley is under, okay, this is a compute valley. This is a city in the US, okay, where that involves two bases. So we are going to create the basin over these two areas, and as well we have two river networks. We have two river basins. Okay, great. And then we have also a raster file. Okay, and this is everything that we need in order to create our model, a seawater intrusion model. Okay, if you are following me, please type 2. If you are following me, please type 2. If you have any questions, let me know. Okay, so let's see. Let's type anaconda prompt. Okay, CD documents. Okay, who is here with me? If you are following as well, please type 2. CD documents regional, CD documents, CD regional. Okay, and then type Jupyter Lab. Okay, Jupyter Lab. Great. If you are following, also type 2. If you have any problem, please let me know. I mean, what is on my reach to help you with any problem. This is my WhatsApp number as well. Okay, if you want to send me a message for a specific thing. Okay, if you are here with me, please type 3. If you are here with me, please type 3. Hello. If you are here with me, please type 3. If you are here with me, please type 3. Okay, great. Great. Okay, so let's see scripts, and then we start with notebook. Okay, and this will be called part 0. Part 0, why? Because when you use Voronoi grids, you have to generate the templates. Okay, Okay, great. So let's generate the templates. Okay, so say from mf6 Voronoi import list templates y copy template. Okay, so we are going to list the templates, and the templates will be, there are only 7, okay, for all the for utils. Yeah, great. So there are only 7 templates for all for 90% of all this. So we have the general Voronoi, so this is a must. Okay, we have the model creation that we are going to use because no, we are going to use the seawater intrusion. And well, depends on the time, but we can do the VTK generation. Okay, but it depends on the time because this can be very. It really depends how you are interacting on the. Okay, because if you are up to me in the typing, we can do the VTK generation, but if you are not, okay, so copy template, seawater intrusion, regional. Okay, so actually this creates shift enter, copy template, VTK generation, regional. Okay, so here we have the 3 of them. Great. So if you are here with me, okay, so what it does is actually creates a copy with this prefix, and the prefix is important because this actually ensures the model that or the project that we are working with. And these are my, my backup folders that I use to give to the webinar. Okay. Okay, if you are here with me, please type 4. Which are your plans for Christmas? What do you, because this is the closest webinar to Christmas that I have organized. Okay, if you are here with me, please type 4. Okay, great. So let's see, let's go to regional generate Voronoi. Okay, so we are going to run the first line. This will be called regional seawater intrusion. Okay, on the pixel size will be 500, and the multiplier will be 1.5. Okay, so this is updated. Okay, so this is different, or this is what you have to, this line was updated. Okay, great. So here we have the basing. Then we have the refinement. The basing is called shapefile, and this is called model aoi.shapefile. Okay, and this is the on the ref. This is shapefile, and this is model ref.shapefile. And this is the size of the refinement is 100. So this is updated. This is updated as well. And then we are going to create another one that is string 1. That this is from Hatari Utils 1. This is one basing delineation. River basing.shapefile. And on the string network it will be 150. Okay, and stream 2. Hatari Utils 2. River basing. $150. Well, pumping wells dot shapefile, and this will be the pumping wells will have a refinement of 50. We have the observation points as well, and this is ops. This is shapefile. This is ops points. Ops points dot shapefile, and the size will be 50. And then we have also the C shapefile. See here the CGHB, and this will be 400. Okay, 400. Great. Okay, so this is the line is in the, okay, if you is on the chat, so great. So if you are here with me, please type 5. If you are here with me, please type 5. Great, Fatima. Anybody needs time? Let me know. Okay, now we generate the distributed points. Okay, this web version, actually I'm not really sure that it will have a web version, but let's see. Okay, so we have the progressive cell size, so we are working with 8,000 cells. That is all right, huh? That is, I mean, it's light. Okay. Okay, great. But we have when we work with many shapefiles, we have a problem of short sizes, and this is a problem that will prompt you an error on the it will prompt you an error on the uh, Fortran. Okay, so that is why we have to check. We have to uncomment this one and say okay, and then we have some cells that have some short sizes. Okay, and then we have to fix those short sizes for a threshold of 0.01, and then we have to check that there are no. Okay, so that was. If you are here with me, please type 6. Okay. Great. So we do. Okay, so we create an output. Okay, so we are going to create an output folder. What does it mean? That here an output folder will be created, and then in this we are going to store the shapefile, the shapefile. Okay, so if there is an output here, and this is the shapefile, the mesh of the shapefile. Okay, great. So that's it. Okay, great. So and then we are going to plot this. If you see, this is our mesh that has all that we have inserted. Okay, great. If you are here with me, please type 7. Okay, and now we read the output. Okay, we read the output. We create a JSON folder, and in this JSON folder we are going to store the. Okay, we run the. We read the JSON. We read the mesh. From the mesh we read the sequences of portings and vertex, and then we save a JSON on a new folder that is going to be called JSON, where we have the information about the number of cells, vertex list, the vertex, the centroid, and so on. Okay, if you are here with me, please type 8. Okay, so we have already our mesh. So now with this mesh we are going to build our seawater intrusion model. So we go here to the P7 regional P7 seawater intrusion. Okay, so we run this. Okay, we run this. We open the JSON. Okay, we open the JSON. We open that. Okay, we run the first 3 cells. Okay, and this will be this is the dem that is modeled, and then we have, okay, we need to do something when we work with seawater intrusion is, okay, follow me. Okay, the problem is that on the borders of the sea, okay, or your dem on the extension of the sea is actually the values of the elevation is not 0. Okay, so and this is a problem because it has to be 0. So in order to do that, we are going to fix the elevation. So in the extension of the sea, okay, the water table will be 0 always. Okay, and this is what we do here. Okay, so in this loop we, okay, from the dem, okay, we apply 0. Okay, if is located under the sea. Okay, so there is a sea beach, which is the one that is sea, no, a sea beach. Sorry, sea beach. Okay, it's beach. Okay, and sea beach is this shapefile. Okay, this is the shapefile that it will be where the elevation is 0. It's not actually in the border. Also, because the seawater intrusion has some. Okay, it's also the, how to say, the where you expect that there is no elevation issues. Okay, why? Because this is an elevation from an Amsterdam, and the elevation from the Amsterdam is really crappy on flat areas. Okay, so that's why the sea beaches also is the sea and the beaches. Okay, so if you are here with me, please type 8, 9. Okay, great, you are doing amazing. Huh? If I really enjoy, I really enjoy. Okay, so the default value is when the bottom aquifer is minus 150, minus 30, but in this case will be minus 150. Yeah. Okay, great. Okay, and then here we do. Okay, so it will, the bottom will be minus 150, and then you are going to see the thickness. Okay, this defines the thickness of the layers. Okay, but this you are going to see on the cross section. Okay, do you have any questions so far? Let me know. You can open the mic. Okay, so if you are here with me, please type 1. So we define the executable. This define the executable. It will continue even that if there hasn't reached any convergence. Okay, and it will work on model files folder. So here it will create a model file. Okay, it's here, but it will. This is where it's going to be. The values are going to be stored, and we are going to work with one stress period of 50 years. Okay, with two stress periods, the first one of 50 years and the second one of 30 years. Okay, this is the initial, and then we have the initial state. Okay, the steady state. Okay, and then we have, this is the transient. This is where we have wells. Okay, so we define these two stress periods. If you are here with me, please type 1. If you are here with me, please type 1. Any questions, let me know. Okay, great. So now we create the flow model, the solver, okay, and the geometry, and then we can plot the geometry. Okay, and here we have the geometry with our mesh. Seems all right. If you are here with me, please type 2. Just to remember that we have a coming course in in pest, that the coming course on pest is in January 13. Okay, so you are invited to follow this course because it will be the only time that we are going to give it live. Okay, so this is the link in case that you are interested. Okay, great. And after the course, okay, it will be in our website in elearning.hatrilabs.com, but as a asynchronous course, okay, so you can take it anytime. Great. So we are going to do the cross section, okay, and let's see the cross section, but we are going to say ax.setGeolim of minus 150 to 100, okay, because we want to plot the most active part, okay, and the formulas that you have for every layer actually are defining these thicknesses, okay, great. So if you are here, please type 2. If you are here, please type 2. Great, Fatima, you are doing amazing. Okay, Paul. Paul, you there? Okay, great. Great. So the initial conditions, everything is saturated by default, and on the K values, we are the values for the first 3 layers will be 4 10 to the minus 3. Then they will be 1 10 to the minus 3 for the next 3 layers, and this is 4 10 to the minus 4. Okay, if you apply a low K, the interaction in between the aquifer and the sea is really small, so the seawater intrusion is, the length is lower, but as well so I mean, this is an hypothetical case, but if you want to see some impact, actually this impact will be applied in a long, I mean, you will require a lot of large amount of years in order to represent the intrusion. Okay, great. So the first 5 layers are unconfined or are convertible, and the second 5 layers are confined. Okay. Great. On the steady state, the first one in the steady state, this has to be false. Okay, the first one is false, okay, because it's steady, and the second one is true. Okay, great. This is false and the second one is true. Okay, great. So if you are here with me, please type 3. If you need further explanation, let me know. Okay, if you are here with me, please type 3. Three, 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 three. Okay, great. So we applied some recharge and evapotranspiration. Okay, and then we define the intersection object. Okay, great. So here we don't have regional flow, so we are actually going to comment this. Okay, so this will be with control. Okay, for every there is a command to do this. Okay, but I don't know where is on your keyboard. I have a keyboard in Spanish, so for me it works like that. Okay, in your country, but otherwise you can insert some hashtags at the beginning. Okay, and this will be C. The only GHB will be the C, that will be interpreted as the layer and the cell, 0 as the elevation, 20 as the conductance, and 0 is the auxiliary. Okay, 0 is the auxiliary, and this will be called C. Okay, great. So if you are here with me, please type 4. If you are here with me, please type 4. Okay, great. So now we are going to discuss. Okay, so we have the GHB, we have the auxiliary of concentration, we have bound names. You need the auxiliary in order to couple the flow and transport. We have an observation dictionary where you have whatever is regional flow, but actually there is no real flow, but we are going to leave it like that. And then we have also the C. Okay, and then we initialize this observation on the boundary condition. Nothing to change here, so we just okay. So we do okay. So we define the by package. Okay, when the concentration is 35 grams per liter. Okay, when the concentration is 35 grams per liter, the density is 1025. Okay, but when the concentration is 0, the density is 1000. Okay. So this is the slope in between density and concentration, and you insert this slope, okay, and then with other man here, and this is how you define the by package. Okay, great. So and then you can plot your general head boundary, oops, for the mf6 for the first layer. Great, so that's it. If you are here with me, please type 5. Okay, great. So now we are going to do, we are going to insert the pumping wells, and the pumping wells in the template are inserted on the first stress, in the second stress period, because the first stress period is designed to be just the steady state, okay, a case that where you don't have any exploitation of the aquifer. Okay, so that is, so we run this. Okay, so, and then there are a lot, okay, I have a problem that this is the shapefile is actually pumping wells.shapefile. Okay, great. So these are the, okay, this is what you have to change. If you are here with me, please type 6. Okay, great. So let's continue. Now what we are going to do, okay, so we have defined the cells, we are going to apply the cell, and then we are also going to find an observation, okay, to those cells, okay, because we want to see the value of the stage of, no, of the pumping rate. Great, so we initialize that, and then we plot the well. So but in order to plot the wells, I am going to copy, okay, so I'm going to copy this, and then I'm going to insert a new cell. Why? Because okay, because ref bounds gpd read file of shapefile model ref.shapefile total bounds. Okay, so we got some bounds, okay, because the problem is that since the mesh is so small, okay, on the regional you are not going to see the wells, so that is why fig ax is equal to plt subplots, okay, m capital V is equal to flopy plot map view of GWF mv dot plot bc of well k is equal to 1, ax is equal to ax, plot all is equal to true, so it will plot all the layers. Okay, then we are going to plot the well GHB k pair is equal to 1, ax is equal to ax, mv dot plot, and this is capital V, capital V, this plot grid of alpha is equal to 0.5, line weight is equal to 0.2, ax dot set xlim ref bounds 0 minus 1000 ref bounds of 2 plus 1000. Okay, this is for the extension, and this is for the while lim 1 and 3. Okay, this is the code on the chat if you get stuck. And if we plot like this, what we are going to have is this plot where we see the boundary condition of the general head boundary, we see the refinement, we see the wells, we see the mesh, and so on. Okay, great. So if you are here with me, please type 7. Fatima. Okay, done. Great, Fatima. Great, Paul. You are making my Christmas here. Okay, so let's see. Now we have to work with the rivers. Okay, because we have rivers. Okay, so here I'm going to insert. Okay, so we are going to work with the river package. Okay, rivers is equal to gpd read file, because there are two shapefiles of river, Qatari utils. One, river basin dot shapefile. Okay, and list of rivers. Okay, the cells that intersect with the rivers for this shapefile will be an empty. Okay, for E in range of the. Okay, and for every part of the shapefile of river dot shape of 0. Okay, for E list rivers dot append of rivers geometry dot log I. Okay, so we got the geometry, okay, and those geometries we create a river MLS multi-line string that is okay. So we are just all the geometries we are compiling in a big geometry that is multi-line string of lines is equal to list rivers. Okay, and now that I have, we got the river cells. Okay, we use the intersection intersect the river MLS cell IDs. Okay, and then this will give us the river cells. Okay, this will give us all the cells intersected with the river basin of the first layer, GPD. Okay, great. So this is on the chat. Okay, once you have those cells, what you are going to do is you get river SPD is equal to a dictionary where the river SPD of 0 is equal to a cell, and say for cell in river cells 2 points river SPD of 0 dot append okay. So on the first layer 0 comma cell in top the cell. Okay, so and it will be the conductance will be 0.01. Okay, great. So and then we define that also for the river category utilities river 2. And then again we just need to do this again. Okay, for the cells intersected with the river basin of the other river basin from category utilities 2, it will also apply that. And then finally we use ref is equal to Flopy dot mf6 dot MODFLOW GWF DRN of GWF stress period data is equal to river SPD. Okay, and then say ref dot plot okay river SPD. Okay, and this is the two river networks in our model. So I will copy paste this code. Okay, this code, okay, this code as well, this code, this code, and then the final. Okay, so with that you create your river network as drainage. If you are here with me, please type 1. Okay, you are doing my Christmas. Well, okay, so now we define the transport model. The transport model is actually, you don't have to do that much because it's the standard for all. Okay, so we define the transport model, the solver, and the discretization that come. Okay, you could create your transport model smaller than the, you can create the transport model smaller than the flow model, and this will be much helpful when you want to model the seawater intrusion, because actually you don't need to model all. Okay, however, I don't know to do that. Okay, in theory this is possible because you can work with 2 discretization. Okay, we are going to work with the same discretization. Okay, the starting concentration is 0. Okay, and when there is when the concentration, when the bound name is equal to C, so it will apply a concentration of 35 as the initial concentration. Okay, so that will create this. Okay, amazing. If you are here with me, please type 2. Okay, I just had to run the files. Fatima. Okay, so there will be advection, dispersion, store activity, and as well a sink and source. But the sink and source will be the okay, so we are not going to apply any sink and source. So we are going to see just the concentration will be our sink and source, because we are going to define the cells that are at the sea, that intersect with the sea, as constant concentrations. Okay. Okay. And now we are going to work with the observation types, where we have the observation and the field of the name of the observation will be name, and the elevation of the observation, okay, the well screen will be LF, and that's it. Shift enter. So then you have this For this cell is at layer 2, 2, 2, 1, 1, 3, 3, and these are all the observations. Okay, if you are here with me, please type 3. Okay, great. So now we have, okay, so we have the head file record. We are going to print for concentration for all of the output for flow will be just on the last, okay, while for the transport will be on all, otherwise you are only going to get in the last one. Okay, great. So, and then we write the simulation. So, and there is a trick here. There is a trick here. Okay. What is the trick? Okay. So first, let's try to run this. Okay. Great. So now we run this, and then if you run, you are going to see something like that. Okay. 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 So I will kernel run up to selected cells to show you the error. Okay. Because the, okay, let me explain. Okay. Okay, great. So now it's okay. So there is a problem here. As you see, there is a problem, and this problem is kind of really stupid. You have to go to model files. You have to go to the mf6Voronoi, and then you have to, in the solution group, you have to change, okay, because the order is first the flow model and then the transport model. Okay, you cannot do that with flow pipe, okay, or at least I don't know how to do it, but you can do it. Okay, then you save it, Control S, and now you can run the simulation. Okay, now the simulation will run. Okay, interesting, isn't that? So you have just to change the order of the solution. Great. Okay, if it's running for you, please type 4.
See, that's what you're asking.
Okay, it's running. Okay, and it has finished. And once it has finished, we can read the flow. For example, for the first stress period, we can plot the flow of the model, the flow model. So this is the flow model. Okay, great. And for the in cross sections as well, this is for the first stress period. Okay, so here we see the heads, and this is at the end of the first stress period. Here you see the this has a reason here, because flow is actually going from this also, and there is a upwards flow. Okay, so the flow is actually trying to reach this zone, so it is charging in this part, so that is why it's going this way and this way. Here you should see like more flow paths in this way. I don't know why. Maybe this is an error, so we have to. So if you plot this for the second stress period, okay, you also have like the intrusion, but this is on the flow, okay, and then you also have the discharge in this part, okay. Okay, now let's explore the concentration. This will be for the first stress period, the second stress period, first time step, and then we plot that. Okay, and then here you see the seawater in, okay, the for the first layer, the distribution of the distribution of concentrations, and then you can see that on the cross section. Okay, you see how the seawater has intruded. Okay, if you are here with me, please type 5. Okay, do you have any questions so far? Do you have any questions so far? Okay, that will be the webinar for today. Just to remember that we have a coming course in PEST, and then you can always be a Patreon from us, and then you support our results. Okay, so this will be the stop of the recording.